这个学分学程，就是各位在座很多同学参与的这个学程呢，我们这学期很幸运的荣获了这个国立台湾大学109学年度的成效卓越学分学程哈。那这个是蛮不容易的。那至少就我所知是全校有4个学程，只有4个学程得到这个肯定跟鼓励哈。所以这是在座的跟学校内、校内、校外很多老师共同努力的这个成果哈。所以也很谢谢这些老师的协助跟长期以来的支持，也谢谢各位同学的参与，让我们有这个机会可以有这个得到这个肯定跟鼓励哈。所以我们这学期也会以这个活动哈当做一个平台哈，会办理一些活动，需要让各位同学更多的参与哈。我目前初步想到的一个就是我们其实中系有设计这个3个很漂亮的这个叫什么？资料夹，好，那有3个不同的款式，所以我们到时候呢会让同学们呢到我们的这个脸书网站上去按赞，然后分享，你就可以拿到1个。OK， 那事实上是希望有更多的同学能够参与啊，不是我们学程的学生也可以这个按赞跟分享哈，一样可以拿到这3个不同款式的。那打卡按赞分享1次可以得到1个哈。那我们之后呢也会安排其他活动来跟大家一起庆祝这个学分学程的这个奖励哦，那当然也会希望说能够让校内外更多的老师跟同学知道我们的这个活动，也知道我们这个学分学程哦。好，那其次呢，就是上次上课有跟各位提到说，我们有这个上瘾科学的特展哈，也是我们这个课程里面如果有修课同学的额外的一个加分的小活动哈。那这个展呢到5月30号为止，所以各位同学如果对这个展有兴趣的话，那请自行到这个台北科教馆7楼东侧，它是特展，但是你只要买一般的门票就可以进去看展哈。那一般营业时间好像到下午的话好像到5点吧，好，所以欢迎大家把握时间，在5月30号之前去看展。那同时也要记得写你的这个参展的心得的部分哈。好。那另外呢，我们在3月24号呢，我们目前正在筹办一个 East Asia Social Brand Symposium 哦。那这个是几位这个包括日本、韩国、新加坡以及美国跟这几个国家的跟做 social neuroscience 有关的老师们办的一个线上的这个 symposium 哦。那目前正在排这个演讲的这个行程。那台大这边呢，至少有我跟这个周明义老师，生科系周明老师参加，都会有一个很短的 talk。所以如果同学们有兴趣的话，也欢迎这个把握这个时间去听这个演讲。那这是一个 virtual 的演讲。那详细的活动流程确定之后，我会再跟大家宣布。那另外一个跟同学们宣布的呢，也是跟老师们报告的，就是说呢，我们这学期呢还是会同样举办这个学生的暑期实验室研修，就是 summer internship 的部分哈。那详细的活动方式会跟各位报告，就是让大家利用暑假的时间，用1个月的时间可以进入到学程老师们开放的实验室去做一个 internship 的这个机会哈。所以有同学们已经有想要去哪些实验室的话呢，或是说想要把握暑假时间到实验室去看看了解一下真正做实验的状况的话呢，那请这个可以先把这个时间先预留下来。那我们之后呢会宣布给这个学程的所有老师。那去年的话我们就至少有19个老师开放他们的实验室哈，所以我们总共有19个实验室可以去选择。但是你要准备一些相关的资料，跟老师做 interview。看看有没有办法可以参与到这个实验室研修的部分哈，所以请大家把握这个暑假机会参加这个 summer internship 的部分。那另外呢，上次忘了跟大家宣布哈，事实上我们这个课程呢，我们也是这个我们中心呢有成立一个与神同行社哈。那这个不是那个上帝了哈，我们的神是神经科学了哈。我们是以神经科学同行的一个社团哈，所以呢，就是说在座的同学都非常欢迎。那我们待会下课时候呢，如果有兴趣参与这个与神同行社的同学们呢，我们会有一些额外的活动让大家参与，以及额外的一些，比如带大家出去哪里参观啊等等，或是说一些额外的活动。那希望透过这些额外活动呢，能够帮助同学们一方面更了解神经科学，另外呢，我们会希望说提供额外的机会，让这个社团同学可以跟每次的讲者有多一些的互动的这个机会，不管是课前跟课后哈。 所以就请有兴趣的同学呢，在这个今天的课程 Q&A 结束之后呢，如果有兴趣的同学呢，那到前面来扫这个 QR code， 然后另外的话，我们会请大家做一个简单的这个记录，我们要约个时间跟大家碰面，然后讨论一下这学期这个社团要怎么样的进行跟一些注意的事项。当然，我会希望说这个是变成是同学们真正的一个社团了哦。那我们只是老师们只站在一个帮忙辅助的角色，希望更多同学能够透过这个社团了解神经科学跟了解神经生物跟认知科学的相关的领域跟老师。OK， 好，谢谢。好，那另外一个呢，就是本学期的这个神经生物跟认知科学专题讨论的课程，或是我们 Neuroscience Monday 的讲者呢，那目前都已经大部分确定哦，还有2位正在联系中。那这是这学期的讲者的部分，所以请大家先把这个时间预留下来，然后看一下，就是说。这是我们这学期会有的这些讲者跟相关的这个日期哈，所以请大家把时间预留下来。然后，如果你是修课的学生的话，请记得这些时间是你一定要出现来参与这个课程的。那如果是旁听对演讲有兴趣的同学呢，也欢迎把握这些机会，踊跃来听讲哈。OK， 那今天的部分呢，就是这个我们就邀请到的第一位讲者哈。好，那现在我就要把它 switch 到英文去后。Okay, let me start tonight's first presentation with my brief introduction about Professor Ken-Ichiro Tsutsui Sensei. This photo was taken when I was in Tohoku University, and as you can see that here is the Tsutsui Sensei, and we went to Zhao, Zhangwang. It's a very famous ski place, not far away from the Sentai city. Okay. Actually, Tsutsui Sensei is my host during my stay at Tohoku University, and actually he's a very wonderful host and a wonderful friend to show me around, and also including to go to Zhao and many places nearby. Tsutsui Sensei currently is the professor in the Graduate School of Life Science at Tohoku University, Dongbei Daxue. He's also in charge of play an important role in the Neuro Global International Joint Graduate Program, which is there's lots of international students, especially PhD students, join this Neuro Global Program. So if you guys are interested in about this program, you can look up to their website and get more information about this Neuro Global International Joint Graduate Program. Actually, 2 years ago, we also sent our students from our center to this to join their Neuro Global Program. Okay, for a week. Okay. So Tsutsui Sensei received his bachelor degree and PhD at University of Tokyo. To be noticed, actually he got the degree from experimental psychology. Okay, so actually he's his training background is in psychology, but he's very interested into the monkey research. After then, he served as a research associate at the Nihon University School of Medicine, and also as a research associate at the University of Cambridge. And his advisor is Wolfgang Schultz, which is a very famous guy for doing decision making, especially in monkeys. So Tsutsui Sensei's research interest is very broad. So that's why I think we get along with each other very well, because we are very broad research interests. So we will talk about lots of research from time to time. So actually in his laboratory, he have to use the monkey as a model and also use rats as a model system. So in today's talk, he will briefly tell you about, maybe he will mention about his research interest, especially from the system neuroscience aspects, to introduce how he get involved in this kind of research. So without further ado, please join me to welcome today's first speaker of our seminar series, Professor Ken-Ichiro Tsutsui.
Okay, thank you very much for your kind introduction, Professor Lai. Can you hear my voice?
Yes. Give me a second. We have to switch to share your screen. Okay, let's go now. Please go ahead.
Okay. And can you hear my voice without interruption?
Yeah, your voice is good. Yeah.
Okay, so thank you very much again for your kind introduction. Yes, it was my wonderful time spending the winter time together with Professor Lai here in Sendai. Now I miss him very much, being alone in my office, but I hope I can see each other again soon. And I'm really also looking forward to visiting the NTU again, and the sites that I saw through this internet cameras today remind me very much about the very interesting experience that I had in NTU when I visited you. Maybe it was a year ago. So today I'd like to talk about one of my research streams on the prefrontal cortex. The prefrontal cortex is believed to be the commanding center of the whole brain, and this, which is especially developed in primates and especially in human beings. And today I'm going to talk about our study using rhesus monkeys. Actually, they were Japanese monkeys, Macaca muscata, which is quite close to what you have in your island, Taiwanese monkeys, but only very slightly different species. And so I did some behavioral study together with the neurophysiological recording and also manipulation. So based on these experiments, I would like to share my ideas about the function of the prefrontal cortex with you today. Okay, these are the people who really did the work, who were working in the lab every day, analyzing the data and writing papers. I was kind of in the office all the time and kind of trying to orchestrate the whole activity. The most part of that I really contributed with the paper writing part, well, the planning part and the paper writing part. I'm sorry for this Japanese language. Maybe only this slide is Japanese, so please forgive me. But you could somewhat guess what's there here. So this slide shows the scheme of the research activity that we have these days. So we have mainly two aspects in our lab. It is surrounded by this blue square or this green square here. One thing that we do is the wide-range recording of the neural activity through neural imaging like this. This is functional MRI, or multiple ECOG or LSD electrodes implanted in the brain. And at the same time, we do some neural tracing study to find out the precise wiring of the brain, because knowing about the details of the design of the neural circuit is the basis of the understanding of its function. So we didn't do these biological or anatomical measurements, as well as we do some manipulation of the brain activity. There are mainly two approaches. One is using transcranial magnetic stimulation, which is totally non-invasive, and another one is opto or chemogenetics. So using these two approaches, we get some empirical data and then try to combine them into one model with the help of computational scientists. So we compare what's normal and what is abnormal in the functioning brain based on the circuit models on this large-scale this scale of very large complicated network. Okay, so let's go into the background of today's talk. So what you are seeing on the screen is the black and white picture of a human brain, cerebral cortex. This is from the lateral side. So this is the left hemisphere, and this is the medial surface of the same hemisphere. So this is still the left hemisphere. So it was turned around 180 degrees. These are the surfaces, original surface, and they are here as well. And only this part, you see, is the cut surface, because this part of the brain is stuck together as one structure in the head. But this part, the cerebral cortex, is originally having this surface on the medial side. So we have almost a symmetrical structure on the left hemisphere and the right hemisphere as a cerebral cortex. And this numbered part of the cerebral cortex is the frontal lobe, which includes the motor cortex, the primary motor cortex, which is numbered 4, or the premotor cortex, higher motor function, which has a higher motor function here, marked as area 6. And what we call a prefrontal cortex is this structure anterior to this premotor cortex. So it includes 44, 45, 47 like this, and also 9, 46, 8, 9, 10. On the lateral surface, on the medial surface, it includes area 9, 34, 32, 11, 12, and 24. These numbers have no meaning, almost no meaning. It is a random numbering by the researcher which studied the cytoarchitecture of the cerebral cortex for the first time, whose name was Brodmann. Please just think it is a kind of nomenclature of different sub-areas in the cerebral cortex. Okay, so as you can see in this figure, this is the same figure but with the different marking. So the prefrontal cortex is this part marked with this these pink lines, and with this green lines is the premotor cortex. The area marked with this purple line is the motor cortex. And this yellow part is what is called a cingulate cortex, which is developmentally a little bit older cortex than the new neocortex is here. This structure here is the corpus callosum, which contains a lot of fibers, which is connecting the right and the left of hemisphere of the cerebral cortex. So the content of this structure is the axons of neurons, which is projecting from left hemisphere to the right hemisphere, or the right hemisphere to the left hemisphere. So all the neurons communicating over this corpus callosum is sending an axon this way down, and then somewhere here, and then goes up to the other side of the cortex. Okay, this figure shows the difference of the proportion of the prefrontal cortex within the whole cerebral cortex. as I have said, this prefrontal cortex has developed very quickly in mammals, and especially in primates. So as you can see, these are very common mammals, cats and dogs. You can see the prefrontal cortex is still very small in cats, or maybe the dog has slightly bigger prefrontal cortex than cats. Their behavior is a little bit more complicated than cats, being more social, pro-social too, and they are very friendly to humans. And as you can see, almost the same proportion of the prefrontal cortex can be seen in the squirrel monkeys. This is the New World monkey. And in the Old World monkey, you can see a slightly bigger proportion of the prefrontal cortex. And its proportion gets dramatically bigger in the chimpanzee, and of course in humans. It occupies, its proportion in the cerebral cortex gets the biggest here, the largest. Okay, the prefrontal cortex, we can regard the brain as the sensory and the motor processor, and it is constantly having an interaction with the environment. So through the sensory organs, we get sensory inputs time by time without any interruption, and the sensory system in the brain processes these sensory information here. On the other hand, in reaction to the sensory input, we are capable to make motor reactions. And through the muscles, through the muscle movement, muscle function, we have some actions towards the environment. And this motor activity is planned and then generated through these motor pathways. And as you can see in this sensory and motor structures in the brain are hierarchically organized. So if the communication of the sensory and the motor part is done in a very lower level of the hierarchy, actually that is the reflex. So the reflex, so some very simple sensory input can generate a very simple motor response here, almost automatically in the nervous system, such as knee-jerk reflex. When you hit your knee, your leg, your knee joint automatically, almost automatically extend. So that's a knee-jerk reflex, and this is one of these reflex functions. But there are many levels, many different levels of this communication between the sensory and motor structures. And the most complicated part is the association cortex here. And the typical example of the involvement of this association cortex for the perception action cycle is language. So when somebody sees you and says hello, you will understand its meaning through the sensory processing, and with reference to the memory, you will judge whether you should say hello or go to hell. So after judgment, you will say maybe hello if you want to be polite. So in this way, everything, every action and every sensory process in your brain can be considered as a part of perception action cycle. And the prefrontal cortex here is the kind of command center of this perception action cycle. So this is the schematic drawing which shows the input source and the output direction. of the information coming in or going out from the prefrontal cortex. So the prefrontal cortex receives information from many different areas in the cerebral cortex, and also from many other subcortical structures, which is amygdala, thalamus, and brainstem, which includes mainly some internal information about your mind or body, such as emotion or gut feelings. On the other hand, the prefrontal cortex has many targets of its information output. Of course, many other parts in the cerebral cortex, as well as many different parts in the subcortical areas, as listed here. Now, I'd like to mention this new technique, transcranial magnetic stimulation, because this somewhat is a core technique that is concerning today's talk. So this was invented by Anthony Barker in UK in 1980s on the basis of a very simple physical law, that is the concerning the electricity and the magnetics. So this shows the basic mechanism, how it works. So we put this coil on the skull in this way, a skull of human or monkey, and through this machine we induce a very rapid and a very huge current flow through the coil, like this. And around the coil, that induces the magnetic field. Yes, in the physics that you learn in the high school, wherever there is a current flow, this magnetic field is induced around it. So, based on that very simple law, you can understand that the magnetic field is induced through around this coil. And actually, that in turn, so, this is a special coil which was invented by the Japanese researcher, a figure of 8 coil, and its characteristic is that the current flow is double here, so the magnetic field around this part is bigger than the other part. And therefore, and that magnetic field in turn induces some current flow in the brain, because the brain this magnetic field can go through the skin or the skull very easily. On the other hand, if you try to put an electrode on the skin and try to pass the current, because of the skin and the bone and intervening liquid in the dura, it is very difficult to stimulate the brain electrically. So rather than directly using the electricity, by using the magnetics, you can easily stimulate the brain in this way, inducing the current flow, which is actually the electrical stimulation. So this is called transcranial magnetic stimulation, but the reality is that you are inducing some small size of current in it. So that's the point of this technique. And by experience, we still don't know the full mechanism of it, but by experience, we know that high frequency repeated stimulation causes the facilitation of the local neural activity, and low frequency repeated stimulation induces inhibition in the local brain activity. So we are using this tool as a means of basic neural experiment to facilitate or inhibit the local neural activity. All right. So one thing that we can do, one very simple thing that we can do is to confirm the location of the somatotropy in the motor cortex. As you can see, the hand area is somewhere around here, and the foot area is somewhere around deep in the middle surface. I can show to my students during the training course, by using this machine, stimulating my whole brain by stimulating this part of the brain, which is the M1 cortex hand area. Just one pulse, it induces jerking movement in my finger or elbow or the shoulder on the contralateral side. And also the same thing can be induced for stimulating this part, the foot area. And this is really powerful method. I can see you one example from my lab, which is not the main theme of today, but it can be very nice, drastic demonstration of the power of TMS. So it has been known in the literature that the human depression is very much related to the abnormality of this ventral anterior cingulate cortex. So the patients with chronic depression show the lower metabolic activity around this area, and also after the long history of being depressive, their brain have reduced volume of gray matter in this area. So what we have tried to do is to inhibit the activity of this brain area using this TMS. So this is the special coil which can reach to the deep part of the cortex. And this coil, on the contrary, can only stimulate the surface. So the target this time was the deep part of the brain, and unfortunately, with the current methodological limitation, we cannot selectively stimulate this deep part. So what we did is to compare what happened with this deep coil stimulation, which stimulates both the deep part and the shallow part, and what happens with this figure of 8 coil, which only stimulates the shallow part. And this time we wanted to inhibit the local brain activity, so we used the low frequency, which is around 1 Hz. The 1 Hz, 20-minute stimulation, total of 1,200 pulses. And the intensity of the stimulation was 150% of the motor threshold. The motor threshold is the intensity of stimulation of a single pulse, which can induce the muscle contraction in the periphery when we stimulate the M1 cortex. All right, and this is the typical picture, which was taken in the normal state and the depressive state. Normally the monkeys are very social like this, but after the inhibition of that area, medial frontal cortex, they become socially withdrawn, and they can spend almost whole day by just looking down with this crunched posture. Here's the video. So this is a female monkey looked after by this Dr. Nakamura. Sorry, this is the male monkey. The male monkey being looked after by this Professor Nakamura. And this is the behavior under the normal state. Yeah, this guy nicely interacts with the stimulation by the humans. But this is after the inhibitory stimulation on the medial frontal cortex. He doesn't want to come close, and he stays in the corner of the cage, and he doesn't really come, even if he tries to attract his attention. And this is a summary of what happened to the monkey. We did a comprehensive study of understanding the state induced by the inhibition of this brain area, the medial frontal cortex, with some behavioral and physical measures. So we saw reduced behavioral activity in the cage, increased cortisol level in the blood, impaired sociability, and decreased motivation to perform a difficult task, and very strikingly, an administration of an antidepressant, ketamine, ameliorated the abnormal behavioral and physiological state above, and the normal almost went back to the normal state. So this is one example that this TMS can be a very powerful tool for the study of the brain. And in this way, we could demonstrate the first case of the monkey depression induced by brain manipulation. All right, this is the true end of the introduction. And from now, I'm going into the details of the study which we did in the monkey prefrontal cortex. So the mental process behind the problem solving was first described by Thorndike, that it is a trial and error process. This is the famous psychologist of that time. So what he did was to put a cat into this problem box. This is a tricky box that allows this animal to come out with a certain manipulation over of the device in the box. In this case, by pressing this lever that opens the door here, allowing this guy to come out and eat the food which is spread around. So whenever a cat was put into this box, they were motivated to come out. And the trick was always the same for the same session. And here is the time elapsed, time needed for this animal to solve this problem to come out for each repeated number of trials. So trial number 1, it took a very long time. Trial number 2, almost the same duration of time. Trial number 5 was reduced to half time, but still it took a long time here. It took almost 20 or 25 repetitions to learn to come out quickly by pressing this the pedal. So by looking at this behavior, the Thorndike concluded that the main process which is happening in the brain in the animal is the trial and error process. And the characteristics of this gradual process, based on the associative learning, is the slow learning curve like this here. This is a gradual process, a slow and gradual process. But there is a contrasting description by Kerber a little bit later. Another famous psychologist who was based on Germany. Kerber, on the other hand, described this abrupt way of solving the problem, that by putting this chimpanzee into this problem-solving situation. So he was putting this guy here. This is the first case. And this guy was looking at the banana hand from the ceiling, not being able to reach there directly. But there were several boxes around on the floor, and what happened to this guy was by looking around this situation, he just suddenly started to pile up the boxes, and then he stepped on it, and then reached out to the banana at the edge. So this was a very short latency, abrupt problem solving by thinking. And we can guess that within his mind around this time, he had a foresight what would be the conclusion, what would be the outcome if he piled up the boxes like this and reached out to the ceiling. So this is the foresight and having perspective. And that is, in other words, called the inference. So there seem to be two contrasting problem-solving adaptation as mechanisms in our mind. So one is trial and error, and the other is insight. They may coexist within our mind. And the difference of these processes is slow and gradual versus quick and abrupt. And more recent, yes, and based on our current knowledge on the brain, we can guess that maybe this slow and gradual learning process is based on stimulus and response association. And on the other hand, this quick and abrupt learning is based on a general understanding of the environment and abstract thinking. More recently, it is described as bottom-up versus top-down, or much more recently, maybe model-free and model-based learning. And with the current knowledge of the brain, we can guess that this slow process may be based on basal ganglia, based on the function of basal ganglia, and maybe this process, very quick process, would be based on prefrontal cortex. Well, this is still a hypothesis, and we have to prove this hypothesis. Okay, about the functional category, this Jerome Bruner, one of the founders of cognitive psychology, argued in his famous book that the being able to use the functional category can be the basis of abstraction and intelligence. Okay, please have a look at this figure. How do you categorize them into two? Right. So maybe some of you have thought that these are food and these items are two. So this is one category and this is another. Okay, that's fine. Or these are something related to kitchen and these are something related to sport. Okay, that's also fine. But the Bruder, it is exactly what the Bruder called functional category. These kind of thinking are functional categories. But what he had also pointed out was that very small children do not think in that way. They base their thinking on the shape or appearance. So they normally put these long things into one category and these round ones into another category. They still don't know very much about the function of the objects, but they only base their thinking on the appearance of the things. So that can be seen in the early stage of development. But normally, when a human being reaches to a certain age, they come to think about category. And this functional category can be the basis of abstraction and intelligence. All right, so in order to put this functional category into the lab-based experiment, we designed a very simple behavioral task. We put the monkey in front of the screen in this way, and in every trial, we presented one abstract figure like this in the center of the screen. And after several seconds of showing this figure, from the spout very much in front of the mouth of the monkey, we gave either orange juice or saline, depending on the figure presented. So this abstract figure here has a role to indicate which type of liquid is going to be delivered, either the orange juice or the saline. And please note that this saline was the saturated saline, which is really, really thick and disgusting to put into their mouth. So of course the monkey didn't really like it. They hated this saline. And on the other hand, they really liked these oranges. So what he was really trying to do was, by looking at these figures presented in every trial, they really, really worked hard to guess whether a drop of orange juice or a drop of saline is going to be delivered from this spout. So this is what happened in the trial. The presentation of the visual cue, and afterwards a certain delay, either juice or saline was delivered. And this is the rule behind the game. So we normally use a stimulus set consisted of 8 abstract figures. In a session of the total of several tens of trials, we kept the stimulus and outcome association consistent. So these 4 figures always indicated the orange juice coming out 1.25 seconds later. And these 4 figures indicated saline to be delivered 1.25 seconds later. And we used these figures randomly in every trial. So in each trial, the monkey had to recall which type of liquid was indicated by each figure presented on the screen. And we occasionally change the rule without any indication. And there are two ways of changing the rule. One is the whole reversal, so reversing all the stimulus-outcome association. And the other was the partial reversal, reversing only 4 of 8 associations. In this case, reversing these 2 and these 2, but keeping these 2 the same and these 2 the same. So this is the partial reversal. Which reversal do you think is more difficult to perform? And that actually depends on the strategy that you are using. If you have a category in mind already obtaining this first session, remembering that these 4 figures have the same function, and these 4 have the same function. This reversal is very easy, because all you have to bear in mind is that this group now is associated with saline, and this group is now associated with oranges. But on the other hand, if you don't have any category in mind, and if you base on your learning on each stimulus outcome association, this reversal is easier, because out of 8 associations, only 4 associations were reversed. What you have to relearn is 4 out of 8. Okay? So if one is having category in mind, this reversal is easier. And if one is remembering each case independently, this reversal is easier. So first thing we did was to compare the monkey's performance in this condition and in this condition. And this is the result. So this is the new learning phase, introducing a stimulus set consisted of 8 new abstract figures. And then this is the first reversal after overlearning in this session, in this initial session. And this shows the result. The whole reversal was completed very quickly, even in the first trial, first block after the reversal. But on the other hand, this partial reversal needed a very long time compared to this whole reversal. So the conclusion is very easy. The monkey needed much shorter time for the whole reversal than the partial reversal, indicating that they were building up the categorical memory during this period and using that memory and knowledge to adapt to this new rule here. Actually, this was already published in 2020. In this 2018 in this scientific report. So if you like to, and we had further 4 additional experiments to this basic experiment. So if you would like to know about the details of our behavioral study, please look at this one. So what happened on a trial-by-trial basis is shown in this figure. So in this trial, one out of 8 stimulus was chosen randomly and shown on the screen. So on the on the basis of the figure presented, the monkey guesses whether the saline or the juice is coming out. So, when the saline was predicted, when the saline was expected, he was waiting for the outcome by his mouth shut to avoid any saline coming into the mouth. But when the orange juice was expected, he waited for the outcome by opening his mouth to judge the orange juice without failure. So this is the stimulus, and this is the response, and this is the outcome. This figure, mouth shut, the outcome was saline, so that response was correct. This figure, mouth open, the outcome was juice, so you can say this response was correct. This figure, mouth open, juice, correct. This figure, mouth closed, saline, is correct. So you can see almost perfect performance in these trials. And here, we reverse the rule without any explicit cue. So you can see the monkey believing that the rule is the same as the previous trial. By looking at this figure, he opened his mouth in this way, waiting for the outcome. Yes, as you can see, before the reversal, this figure was indicating oranges. But after the reversal of rule, of course, this is now indicating saline. So saline went into his mouth very much unexpectedly. And of course, this response was an error. But you can see, after making this single error, the monkey could perfectly adapt to this situation to any of other figures in the stimulus set. Please note that they were seeing these figures for the first time after the reversal. So actually, this association, for example, this figure predicting saline was the first experience for him after the reversal, because this was associated with oranges in the previous rule. Even though he could respond correctly to this one. And this is the behavioral sign that he was making inference or having a prospect of what would happen with the stimulus of with the other members of the stimulus set. So this is the inference behavior. And as you can see, typically with only one error, he could adapt to a new rule like this. So this is the situation under the whole reversal, shown by this trace here. But under the partial reversal rule, they performed very bad in adapting to the new rule, of course, because there was no cue or no law which enables them to make any foresight. So they had to adapt to a new situation by trial and error. Okay, by inhibiting the function of the prefrontal cortex, we saw what happens to the performance. So the hypothesis was that the prefrontal cortex is performing the top-down inference, but not the bottom-up adaptation. And this is the result. Dotted line is the original performance of the thick line is the performance after the TMS on this area, inhibiting the function of, inhibiting the local neural activity of the area around here. So for the new learning, as you can see, there is no effect at all of inhibiting the function of this area. Only at the whole reversal, but not the partial reversal, you see the reduction of performance here. So by the inhibition of the prefrontal cortex, the new learning of stimulus response association, or the trial and error relearning of the associations, were not influenced at all. The category-based top-down way of controlling the behavior, the inference, was impaired. And we saw the same results by inhibiting the ventral prefrontal cortex, but we didn't see any change of performance at all by inhibiting the dorsal part. So this dorsal part works as a built-in control that only the sound of the clicking sound of the coil or some stimulation of the skin doesn't really induce the behavioral change. This behavioral change is based on the change of the local neural activity of dorsolateral prefrontal cortex or the ventrolateral prefrontal cortex. Okay, so this is the summary of this part of the talk, and I can see that I'm running out of the time. So in the remaining 10 minutes, I can make this. The summary talk about what we found in the neural activity. So we recorded the neural activity of the prefrontal cortex by while the monkey performed this whole reversal. Unfortunately, we didn't really try recording the neural activity by using the partial reversal. So this neural activity story is only based on the recordings under this condition. By looking at this slide, you can see that actually the structure of this task can be explained in this way. There are three major dimensions in the group. One is whether the stimulus belongs to group A or group B. So the category sensitive neuron may respond to this group or the other group B. So if we see a neuron which is responding in this way under the rule X and this way under the rule Y, we can say the neuron is coding the group. And if a neuron is responding in this way, always active under rule Y X and inactive under the rule Y, we can say that the neuron is coding the rule. And if the neuron is responding in this way in the rule X and this way under the rule Y, we can say that this neuron is coding the outcome in this way, the juice. And we looked into the responses of every neuron during this task performance. And this is the logical structure of the task, which can be described as exclusive OR logic. So when the category is A and when the rule is X, then the outcome should be juice. And if we describe category A, B by 0 and 1, and if we describe the rule X and Y as 0 and 1, and outcome juice or saline by 0 or 1, we can describe 4 different situations in this way. And you can see that 0, 0 leads to 0, 0, 1, 1, 0 leads to 1, 0, 1 leads to 1, and 1, 1 leads to 0. This logic is the exclusive OR. So the task structure of this one is very much simple and logical. That actually one has to have an exclusive OR logic in the brain in order to adapt to this rule change very quickly. Okay, and this is one example, a typical example of a neuron which we recorded from the prefrontal cortex. These are the responses to each stimuli under rule X. And these are the responses under rule Y. You can see that this neuron, specific neuron, is always responding strongly to these 4 stimuli, regardless of the rule change. So you can say that this is a typical neuron with its coding category. This neuron is always responding strongly under this rule Y rather than rule X. So this neuron is coding rule. And this typical neuron is coding outcome, in this case saline. So we could find a very beautiful example of the typical information representation in each neuron. But of course, these are very typical examples, and many of the recorded neurons are kind of a bit more messy in the representation of information. Like this, in this way, this neuron is only responding to these stimuli. So based on the statistics, we divided the neurons into 4 groups: the category type, rule type, contingency type, and intermediate type, and plotted each neuron on the surface of the brain in this way. So each dot represents each neuron. You can see that these neurons are almost evenly distributed over the surface of the prefrontal cortex. A slight difference is that the category neuron tended to be a little bit on the ventral side. The rule neuron tended to be around the principal sulcus, and the other 2 types of neurons were widely distributed. And this is the figure putting the amount of information, putting each neuron onto the information place, 3D information space. So we can calculate how each neuron have 3 different types of information in their firing pattern. So if a neuron only has the contingency information alone, that the neuron should be plotted in this corner. And it's the same for the other dimensions as well. So as you can see, every neuron can be plotted in the space formed in this way by 3 axes like this. And the blue dots represents the rule neuron. The red dot represents the category neuron. And this green dot represents the contingency neuron. And this yellow dot represents the intermediate neuron. You can see that the intermediate neurons are intermediately distributed between these clusters of rule, category, and contingency. And we took the average position of these neurons time by time. And this is how these points move during the trial. Yeah. So I will repeat. Please have a look at this one. This is shows what is now happening on the screen, and this is the representation of the neurons plotted on this 3D space. So when the trial started, only these rule neurons and intermediate neurons are active. But immediately after the presentation, the category neurons get active, and then you see a quick move of these intermediate neurons towards the ending point. And its ending point is the contingent. You can start to see the cluster of contingency neurons. Yes. So this analysis indicates that there are 3 types of very stable representation of information coded by different group of neurons, the category and the rule. And maybe this intermediate neuron is somewhat integrating these 2 information and leading some conclusion that is the contingency or the outcome. So this is the trace of the position of each neuron, the average of the position of each neuron by time. You can see only the intermediate neuron is moving. So we can somewhat understand or build up a simplified model of information processing in this way. So by the presentation of the stimulus itself, the prefrontal cortex gets the information that which category that specific stimulus belongs to by with the reference to the long-term memory may be stored in the intratemporal cortex. And over the time, even in between the trials, the rule coding neuron hold the information of the rule over the trials. And when these 2 different types of information became available, this the integration process by the intermediate neurons will start. So this is the logical process of combining the information of category and rule. And a certain conclusion is set in a very short time. So this model was first proposed in our paper around 5 years ago. And please understand, please remember that this calculator is actually based on a very clear exclusive OR logic. So we collaborated with the computational group in Tokyo University to model these different types of neurons into a neural network and tried what happened with these neurons. And the result was, this is the output of the neural network, that we could see exactly the same performance of neurons. So the result of our neural recording together with this modeling research indicates that this kind of logical process is somewhat installed and realized in the neural circuit of the prefrontal cortex. So the summary of conclusions here. All right, so this is the end of my talk, and thank you very much. Maybe it was a bit bad proportion of time for the former half and the latter half, but I hope you enjoyed my talk. Thank you very much.
Okay, Ken, thank you very much for your wonderful talk. I miss your voice and the great time with you. Okay, so now this talk is open for discussion. For if there's any question, please feel free to raise your hand. 大家有没有什么问题 ？Okay, please.
Hi Ken, thanks for the great talk. For the first TMS study you showed us, right? Did you also measure any physiological changes in those monkeys' brain? Because, I mean, of course we can see that, they show depressive behavior, but then do you have any, physiological data to support that claim?
Right, yes, that's a very good question. We didn't do the recording simultaneously, but as a separate experiment, we're doing a basic study of understanding the basic mechanisms of how this repeated TMS works. So what we basically found was a consistent change of the resting state ECOG activity after repeated stimulation. So basically what happened with the low frequency stimulation is the reduction of beta band power in ECOG. We still don't know what that really means, but that was a very consistent phenomenon.